The Earth's atmosphere may look empty, but it's really a complex and dynamic place, swirling with gaseous matter and thermal energy. Some of its most spectacular activity is best viewed at night. If you've ever watched a lightning storm or a meteor shower, the breathtaking aurora borealis in the north, or the shimmering aurora australis in the south, then you know what an incredible light show the sky can put on. But in recent years, with the help of highly sensitive cameras, researchers have been able to document a number of unusual, previously unrecorded light-producing phenomena. These occurrences, which happen high in the Earth's atmosphere, are known as transient luminous events. What are these strange phenomena? Why are they so elusive? And what can they teach us about the hidden workings of our atmosphere? I'm Alex McColgan and you're watching Astrum. Join me today as we look at incredible images of transient luminous events, as we explore and unravel some of the most mysterious and elusive phenomenon in the night sky. Let's begin with a remarkable image. It looks like a cross between a lightning storm and a jellyfish, doesn't it? This is a red sprite, and the formation you're looking at is fittingly called a jellyfish. It's incredibly big, spanning up to 50 kilometers, and originates at an altitude of 70 to 80 kilometers above the Earth. Sprites are short-lived events, lasting 3 to 5 milliseconds, and they travel downwards at blazing speeds, reaching 10% the speed of light. For years, sprites were only rumored to exist. Reports can be found as far back as the 18th century, but a theoretical basis wasn't published until 1925, when physicist C.T.R. Wilson speculated that electrical breakdown could occur in the upper atmosphere. However, despite years of unverified sightings, it would take more than 6 decades for their existence to be confirmed. So, what are sprites? Unlike lightning, which is extremely hot, sprites are cold plasma events, much like the reaction inside a fluorescent tube. Let's think about that fluorescent light for a moment. It requires a power source to ionize the gases trapped inside in order to emit light. As it happens, sprites also require an electrical discharge to trigger their fluorescent reaction. You see, inside a storm cloud, there is friction between rising ice crystals, which become positively charged, and sinking soft hail particles, which become negative. These positively charged crystals, in turn, cause a negative shield layer to form in the air above them. When a positive discharge happens in the form of a lightning strike, the cloud becomes neutralized, but the negative shield layer remains. We now believe it is this unstable, negatively charged shield layer that causes electrical breakdown in the upper atmosphere, producing sprites. It is even possible that sprites aren't especially rare. What makes them incredibly difficult to observe is that they occur high in the ionosphere, where they are often hidden by the storm systems that produce them. So, to see a sprite, you need a clear sightline over a thunderstorm, or perhaps a camera positioned above it. As you can see here, the International Space Station was lucky enough to get one in action. Sprites glow red because under the low pressure conditions where they originate, nitrogen emits low frequency red light where its molecules get excited. Compare this to auroras, which are usually green. That's because at the higher elevation where auroras occur, Earth's atmosphere has greater levels of oxygen, whose molecules fluoresce green when they get excited. But sprites don't always produce red light. Sometimes a sprite will set off a secondary event at a lower elevation. These secondary events, or tendrils, often appear blue. While their light is also produced by nitrogen, the higher pressure causes them to glow blue and near ultraviolet. As a result, some larger sprites, like the jellyfish we saw earlier, have a remarkable appearance, glowing red at the top and blue at the tentacles. Sprite tendrils aren't the only TLEs with a bluish tint. This event is known as a blue jet. Discovered only recently, blue jets are a distinct phenomenon also initiated by storm systems. In these events, the positive charge at the top of a storm cloud forms a leader with a negative shield layer above the cloud, producing a discharge that propagates upwards. This excites the nitrogen, making a spectacular cone-shaped jet that glows blue. Why blue? Well, remember what we said about how atmospheric pressure affects excited nitrogen gases. Blue jets occur much lower in the atmosphere than sprites, which is why they fluoresce a different color. There are also smaller TLEs called blue starters, but scientists believe they are simply failed blue jets. These diminutive cousins only reach 20 kilometers above the Earth. At the other end of the family is a separate phenomenon known as the gigantic jet, and it occurs much higher in the atmosphere, which is why the upper portion changes color from blue to red. We'll leave today with one of the rarest and least understood TLEs. These green or red phenomena are known as ELVs, a quaint acronym that stands for a mouthful. Its full name is Emission of Light and Very Low Frequency Perturbations due to Electromagnetic Pulse Sources. Try saying that 5 times fast. Unlike sprites and jets, ELVs are diffuse, ring-shaped phenomena that occur even higher in the atmosphere. And unlike what the name suggests, they are huge. ELVs can grow up to 400 kilometers in diameter and occur 100 kilometers above the Earth. But despite their size, they are extremely short-lived events. They only last a millisecond, so brief that they can't be seen by the naked eye. While little is known about ELVs, we believe they are caused by an electromagnetic pulse produced by the discharge of an underlying thunderstorm. So, there we have it. An introduction to some of the most spectacular transient luminous events that have been confirmed in recent years. What other luminous phenomena may be lurking in the Earth's atmosphere? It's tantalizing to think about. And because this is still a fairly new field of research, we can only imagine what new surprises may be in store for us. Want more videos about weird atmospheric phenomena on Earth? Let me know in the comments. Picture the ocean on a dark and windy day. Rather than smooth rolling waves, the surface is rough and choppy, with deep troughs and frothy crests. Now, imagine that stormy ocean flipped upside down and blanketing an entire sky. It may sound crazy, but that image is a pretty close approximation of Asperitas Clouds, an extremely rare cloud type that was only recognized by the World Meteorological Organization in 2017. Asperitas, which translates to rough and uneven, is one of the rarest cloud forms on record, and the only one to have been formally added to the WMO's Cloud Atlas in almost 70 years. Given how recently they were discovered, not much is known about how or when Asperitas clouds form, although we have some theories. So, what makes Asperitas clouds different? Why haven't we noticed them before? And could their discovery provide a blueprint for identifying extremely rare weather events in the future? I'm Alex McColgan, and you're watching Astrum. Join me today as we look at spectacular, high-definition images of Asperitas clouds, learn what scientists think could be giving them their dramatic appearance, and explore the exciting implications of this unusual convergence of citizen science and trailblazing research. In 2006, Jane Wiggins, an amateur photographer located in Cedar Rapids, Iowa, took a photo from her office window that she described as looking like Armageddon. She sent the image to the Cloud Appreciation Society, which posted it on their website. The photo immediately set off shockwaves among cloud watchers, who suspected that it could be evidence of a previously unknown cloud formation. Other amateur hobbyists using the Cloud Spotter mobile app started sharing their images with each other, sharing weather conditions to look out for to help others see it for themselves. This caught the eye of the Royal Meteorological Society, which used dozens of photos collected by the Cloud Appreciation Society to prepare a case that they sent to the World Meteorological Organization. After several years of debate, the WMO made an announcement. For the first time since 1951, they were adding a totally new type of cloud to the Cloud Atlas, giving Asperitas Clouds the unique distinction of being the only cloud type to have been discovered as a result of digital crowdsourcing. But why was this rare? And who decides what makes a cloud form unique? Let's start with a primer. Clouds, essentially, are liquid droplets or solid particles suspended in the atmosphere of a planetary body. While on other planets, clouds can be made of methane, ammonia, or even sulfuric acid, here on Earth, the vast majority contain liquid or frozen water. And personally, I'm glad we don't have many of the sulfuric acid variety. Clouds form when saturated air reaches its dew point, the temperature at which, under a given set of barometric conditions, water vapor condenses into liquid due to cooling air or increased saturation from an adjacent water source. There are 5 primary cloud types: stratus, cumulus, stratocumulus, cumulonimbus, and cirrus, each of which are subdivided into different genera based on altitude. However, in addition to these primary categories, there is a range of accessory clouds, which are clouds that become detached from the original genus clouds, as well as supplementary features. All of these are formally classified in the WMO Cloud Atlas, the International Manual for Cloud Identification, which uses a Linnean nomenclature that has been in place since the 19th century. The WMO is responsible for updating the Cloud Atlas, but revisions are extremely rare. The last new formation was Cirrus Intortus, added back in 1951. Now, Asperitas clouds are thought to be mostly a supplementary feature of stratiform clouds, which are low elevation layered clouds without vertical development, although Asperitas have also been observed to be stratocumulus or altocumulus. Interestingly, while the bases of the stratiform clouds are generally flat, they tend to develop significant features at the top due to wind and temperature changes. This is extremely common, and something you will no doubt be familiar with if you've looked out of the window of a plane. What makes Asperitas clouds unusual is their highly developed structures at the bottom. In 2017, researchers from the Cloud Appreciation Society, University of Reading, and McGill University published a paper attempting to describe the features and causes of Asperitas cloud formation. According to the authors, Asperitas clouds are defined by their rough, somewhat wave-like cloud base that lacks the smooth, undulating shape of the, possibly related, undulatus cloud type. Given these semi-wave-like characteristics, the authors hypothesize that Asperitas clouds are likely created by weak oscillatory activity. There are a few potential causes of this. One is orography, which is the wave-like movement caused by the flow of air over mountainous terrain. However, there could be other reasons, such as horizontal wind shear, convection, which is the exchange of matter or temperature between fluid bodies, or atmospheric gravity waves. By the way, in case you're wondering, a gravity wave isn't the same as a gravitational wave. As much as I love space-time physics, we're not talking about massive ripples in the space-time fabric here. A gravity wave occurs at the border between one fluid and another, when a force upsets the equilibrium and gravity tries to restore it, which produces a back and forth movement, or wave orbit. Some familiar examples of gravity waves include tsunamis and the changing tides. You have probably seen the result of gravity waves affecting clouds too, undulatus clouds. I'm sure you've noticed cloud formations like this before from a ground view. The view from space is equally spectacular. But Asperitas clouds have an appearance of roughness that indicates unusual instability at the cloud base. These aren't smooth and wave-like like the undulatus cloud type we've just looked at, but have a formation that is chaotic, like the stormy ocean we talked about earlier. While stratiform clouds often have what is known as Kelvin-Helmholtz instability at the top, an instability that comes from velocity shear within fluids, This instability is more unusual at the base of clouds. So what might be the cause? We don't know yet, but the authors of the 2017 paper from earlier suggest that this instability may propagate downward from the top of the cloud, which could happen if the cloud is thin enough. Perhaps there are different reasons each time. The scientist who captured this time-lapse said that here, gravity waves were moving through an inversion underneath an elevated region of instability. You've probably seen an inversion before, where clouds or even smog is trapped under a layer of hotter air. Thunderstorms were in the forecast, but the thunderstorms could not pull their inflow air from near the surface due to the inversion, so instead, they pulled from above the inversion. The gravity waves moving through the inversion created enough lift that a strong updraft was formed, and it moved in phase with the peak of the gravity wave. This enhanced lift from the updraft increased the amplitude of the wave and made the Asperitas cloud here very visually impressive. Regardless of how it happens, this internal instability appears to disrupt the weak oscillatory activity at the base, resulting in the rough, choppy appearance. So, when you think about it, the winds and currents causing the choppiness of the ocean on a stormy day aren't that unlike the chaotic forces scientists think are producing instability in an Asperitas cloud. In both cases, complex fluid dynamics are in play, giving rise to eerily similar characteristics. Nature may not repeat itself, but it often rhymes. So there you have it, a primer on one of the newest and least understood cloud types on record. If this interests you, you might want to keep watching the sky and taking photos of anything interesting you see. Who knew we'd still be discovering new cloud types? What else out there don't we know about? And who knows, you could be part of the next scientific breakthrough. When it comes to talking about the universe, I'm not usually at a loss for words. But every so often, I see something so awe-inspiring and unusual that words don't do it justice. And it seems that when I posted an image of this last year, it looks like I'm not alone here. Such is the case with Noctilucent Clouds, a strange and beautiful phenomenon that occurs high in the Earth's mesosphere and requires a unique set of conditions to form. In fact, these cloud formations are so captivating that they've inspired communities of watchers who share atmospheric data online in the hope of seeing one for themselves. So, what are Noctilucent Clouds? What gives them their ghostly luminescence? And what surprising insights can they offer, not just about Earth's atmosphere, but perhaps the future of our planet? I'm McColgan and you're watching Astrum. Join me today as we view spectacular images of these eerily beautiful cloud formations, learn how they form, and understand why they are giving scientists a surprising window into Earth's changing atmosphere. Imagine a clear summer night. The sun has dipped below the horizon and Capella is shining brightly to the north. Suddenly, a bright streak erupts low in the northern sky. It might look like a shining silver thread, or perhaps an icy blue whirl. Slowly, the streaks get brighter and clearer, until finally, the whole sky glistens with a patchwork of eerily shining clouds. Night shining clouds such as this formation, photographed over the Baltic Sea, are truly spectacular. And no, they don't actually emit light. They get their glowing appearance by reflecting solar radiation during astronomical twilight, when the sun is between 6 and 16 degrees below Earth's horizon and remnant light is scattered in the upper atmosphere. Because Noctilucent Clouds form at very high altitudes, around 76 to 85 kilometers above the terrestrial surface, they can reflect the sun long after an observer has fallen into Earth's shadow. So, while Noctilucent Clouds also form during daylight hours, they are only visible to the unaided eye at night. To make a Noctilucent Cloud, you need water, dust particles, and incredibly low temperatures. Unlike normal clouds, which form in the Earth's troposphere, where 75% of the atmosphere's mass and 99% of its water vapor occurs, Noctilucent clouds form high in the upper mesosphere, which is the atmosphere's third layer above the stratosphere. Just a reminder, the lowest layer of atmosphere on the Earth is the troposphere, the boundary of which is the tropopause, then the stratosphere, stratopause, mesosphere, mesopause, thermosphere, thermopause, and then finally the exosphere. For more about all these layers, check out this video. The mesosphere is a tricky region to study since it's too high for spacecraft to fly and too low for orbital spacecraft due to atmospheric drag. Noctilucent clouds form slightly below the mesopause, which is the upper boundary between the mesosphere and the thermosphere. The mesopause is also the coldest region of Earth, with temperatures that can plummet below 100 degrees Celsius. By comparison, the coldest temperature ever recorded in Antarctica was minus 89.6 degrees Celsius. These frigid conditions produce tiny ice crystals less than 100 nanometers in diameter, which then gather on dust particles. Researchers have learned that the mesosphere must reach minus 120 degrees Celsius for these ice crystals to form. That's pretty cold. But if noctilucent clouds require such cold conditions, why do they occur during summer? Well, one unusual property of the mesopause is that it is colder in summer than in winter. Known as the mesopause anomaly, this happens because hot air in the lower troposphere expands, resulting in upswelling gases that decompress in the mesosphere, causing adiabatic cooling. Because noctilucent clouds require very low temperatures, they only appear for 60 to 80 days out of the year, peaking around 20 days after the solstice. If you want to see a night shining cloud formation, you'll need a lookout spot between plus or minus 50 and 70 degrees latitude. Although satellites have spotted many mesospheric clouds north of the 70th parallel, here on Earth, the polar regions have too much ambient light during the summer for optimal viewing. So if you happen to live in northern Norway or Alaska, you'll have to travel south for your noctilucent cloud watching. That's a pretty good survey of what we know, so let's talk about what we don't. Saying the mesosphere is a very dry place would be a bit of an understatement. In fact, it is 1 million times drier than air from the Sahara Desert. Not exactly a place you'd expect to find clouds. We currently think upswelling air from the troposphere is the likely cause of this moisture. More puzzling, however, is the question of where the dust is coming from. One theory is that it comes from space in the form of debris. The Earth gets bombarded daily with thousands of meteorites and other space debris. Could they leave enough dust to create such massive cloud formations? Or could there be other causes? Interestingly, noctilucent clouds were first sighted in 1895, 2 years after Krakatoa's massive volcanic eruption in Indonesia, which spewed debris into the upper atmosphere. It has to be something big like this, because otherwise the atmospheric layers don't mix very much, and so dust wouldn't usually make it to the mesosphere. We also know that man-made sources, such as exhaust from space shuttles, can sometimes trigger noctilucent clouds, such as a 2014 incident when the SpaceX Falcon 9 caused noctilucent clouds over Orlando, Florida. In 2009, the United States Naval Research Laboratory successfully created an artificial noctilucent cloud using exhaust particles from a suborbital sounding rocket. And in 2018, the University of Alaska created a noctilucent cloud by releasing water from a suborbital rocket. But without such proximate causes, the source isn't easy to pinpoint. Luckily, NASA has launched a satellite known as the Aeronomy of Ice in the Mesosphere, or AIM, to answer these and other pressing questions. It was first launched in 2007, but as of 2022 is still operational. AIM is powered by 2 solar panels and is equipped with 3 payload instruments: the Cosmic Dust Experiment, which emits pulses to measure speeding dust particles; the Cloud Imaging and Particle Size has 4 cameras that image mesospheric clouds from variable angles to create a detailed 2D panoramic view; and the Solar Occultation for Ice Experiment, which measures particles, temperature, and atmospheric gases in order to identify chemicals and conditions for Noctilucent Cloud formation. There have also been several experiments to synchronize AIM's observations with those of low-flying aircraft, the first of which was conducted in July 2009. By synchronizing data between satellites and aircraft, scientists can construct far more detailed models of mesospheric cloud formation and their features than they could from AIM alone. For NASA and other atmospheric researchers, answering these questions is no idle matter. The mesosphere is a remarkably sensitive indicator of changes that are happening elsewhere in the atmosphere. The same features that make it so unusual, its rarefied gases and sensitivity to changes far down in the troposphere, make it a useful canary in the coal mine, so to speak. Decades of Noctilucent Cloud study have made it clear that they are becoming more frequent, and climate researchers are now beginning to link changes in Noctilucent Cloud distribution to global climate change. As the troposphere gets hotter, the mesosphere, vis-a-vis the mesopause anomaly, may well be getting cooler. And improving our understanding of the mesosphere has other far-reaching implications as well. It is a vital part of the atmosphere for re-entering spacecraft, and because the mesosphere is so dry and low density, studying it could help us learn about atmospheres on other planets such as Mars. By deepening our knowledge of the mesosphere, researchers hope not only to understand the properties of Noctilucent Clouds, but also Earth's atmosphere as a whole and how it is changing over time. They are watching you. Ever feel that prickle across your neck? That ominous sensation of eyes on you, but you can't detect anyone around? Well, although they can't spot the culprit directly, your senses might be onto something. The Earth is surrounded by eyes, studying you, tracking you, trying to understand every aspect of your day-to-day life. They are our own satellites, and there are hundreds of them. And I don't think we have quite realized how good they've gotten. There are satellites with mirrors the size of Hubble's, not pointed at distant galaxies to unravel their mysteries, but staring down at you. There are satellites that can see through clouds and don't care if it's day or night, they see just as clearly either way. In this age of information, where companies are pushing for more and more data, and governments strive to keep track of criminals and threats, the thing that might be harder and harder to find is privacy. Are the benefits worth the cost? I'm Alex McColgan, and you're watching Astrum, and it is time to look out the nearest window and smile for the camera. There. Now, do you want to see how your picture turned out? In 1957, the number of artificial satellites in space first ticked up from 0 to 1. Sputnik 1 was launched by the Soviet Union, officially to practice their satellite deployment methods and to send test radio signals through the atmosphere, but also to show the world that they were winning the space race. The world, however, did not take long to catch up. In 2007, 50 years later, there were 912 active satellites orbiting the Earth. As a testament to how quickly the industry is growing, it took only 10 years for that number to reach 1,778. In 2022, the number hit 6,905. And this number is set to grow. The company SpaceX alone wants to eventually raise the number of active Starlink satellites to a whopping 42,000. In the next 10 years, there could be hundreds of thousands of satellites from various different countries and private organizations orbiting our planet. Of course, not all of these satellites are there for observation. Around half of the ones active right now are communication satellites. But still, according to data collected by the UCS, the aptly named Union of Concerned Scientists, at the start of 2022, there were 1,052 eyes looking down on us. That's a lot of eyes. And they're getting sharper. Let's discuss spatial resolution. This is a measurement of how many meters on the ground are represented by a single pixel in a satellite-taken image. The early cameras on satellites like Landsat 1 had a resolution of 80 meters, which is to say, a single pixel represented an 80 by 80 meter square, meaning you could almost fit an entire football field in it. This made them good for taking sweeping images of our planet at large, and perhaps for keeping track of massive objects like clouds and weather fronts, but there was hardly the sense that our privacy was at risk. Now? Well, see for yourself. These full color videos were taken by Carbonite 2, a commercially available satellite that captures an entire 5-kilometer swath as it passes by at 500 kilometers in low Earth orbit. The resolution for this video is 1 meter, which is good enough that you can pick out details like the motion of waves on the sea or cars driving along the road in real time. Although you might not be able to distinguish their car make and most likely not their drivers. The advantages of such a video are obvious. Transport officials can keep an eye on traffic congestion, and it becomes easy to track the speed of urbanization. There are also numerous scientific benefits, which we'll get into later, but there's one undeniable feature of such improved resolution that made it very interesting for governments around the world. And the main reason you might be worried, it becomes easier for spy satellites to keep track of you. Spy satellites have also come a long way. Originally, when the CIA began their secretive Corona project, disguised as an innocent space exploration program called Discoverer, satellite cameras were recording their images onto actual film, which then had to be jettisoned and parachuted back down to Earth, where the capsules carrying the sensitive data could later be recovered. One of these capsules was actually the first ever man-made object to be recovered from space. It wasn't the most efficient system, and spy satellites tended not to last longer than a year before they ran out of film and capsules. Now, everything is digital, significantly improving the lifespan of such satellites. As for what they can see, well, for obvious reasons, governments tend not to reveal how good the resolution is on their spy satellites. However, it's interesting to note that the video I showed you earlier of the 1 meter resolution satellite camera is not the best the market has to offer. Other satellites boast 50 centimeter and even 25 centimeter resolutions, and some, such as Umbra's SAR satellite, claim to have reached 16 centimeters. And this is only about as good as they are legally allowed to get. The United States has laws in place that make it illegal to have satellites with better resolutions than that, although companies are pushing for this restriction to be lowered, so that they can keep up with a competitive global market that doesn't always have such restrictions. Take a note of that though, this is not about capability. True, the laws of physics put some constraints on us that make better resolutions difficult to impossible without having a satellite fly close enough to the planet that atmospheric drag will start to cause it to fall, or without making a light gathering mirror so large that it becomes difficult to launch them on a rocket. However, it's not accurate to say that spy satellites can't get better resolution. There are rumors of resolutions hitting at least 10 centimeter resolution, perhaps even 1 centimeter. Rumors that were at least partially confirmed by the previous US President Donald Trump by accident in a tweet he posted. In 2019, Iran attempted a rocket launch that ended in failure. Trump felt it was necessary to tell the world that the US government had not been involved in sabotaging the rocket launch. To prove his point, he included a photo of the damaged launch site, hoping to show that there were no signs of foul play. This may well have been true, but intelligence experts around the world were stunned at the crisp detail included in the image. After analysis, it was revealed that the image had to have been at least 10 centimeter resolution, perhaps even better. Let's get a feel for what an image better than 10 centimeter resolution might look like on a regular high street. This is the bit where you might need to wave to the camera. This image is not a satellite image, but was taken by a plane flying over the town of Zurich. However, it does reveal what a better than 10cm resolution image can show. We are no longer on the resolution of making out cars. Here you can see the branches on trees, even the colour of clothes on people. You can see a lot of detail. Can you imagine what a 1cm image might look like? This represents technology that exists today. In fact, better technology is now out there. The satellite that took this is a Keyhole 11 spy satellite. A Keyhole 12 already exists, which amateur astronomers have managed to image in spite of official pictures naturally not being released to the public. We don't know the resolution on this one, but it has dimensions similar to the Hubble telescope, and one of the reasons Hubble used the mirror size that they did was because they realized they could use the same supplier as the US Department of Defense. So there are potentially 11 additional Hubbles out there. Imagine how much further we would be if they were used for science instead of spying. We are also no longer in an era where cloud cover or nighttime can ensure privacy. Synthetic aperture radar imaging is capable of piercing through clouds, as the technology doesn't collect visible light, but instead sends down a radar pulse and then times how long it takes to bounce back. Done enough times over a wide area, with some sensitive equipment to discern the different times taken of different parts of the wave to return, SAR satellites can form detailed physical models of the ground and can even simulate having a much larger mirror than they can actually carry. Because they are not reliant on natural light but are sending their own pulses, these types of satellites can work during the night as well as the day. So, with all of this, you likely are starting to feel a little worried for your privacy. It's unsettling to think that at any time you step out the house, eyes could be on you, watching you walk or drive to your destination, seeing who you meet, where you go. They are probably not able to read your phone screen, but that's not far off. The cost of privacy feels huge. If you live in a city like London, you may have been thinking this anyway with the number of cameras around. But even where there are no cameras, you aren't safe. However, it should be pointed out that satellites with decent resolution, although probably not at the 10cm mark, can be extremely beneficial for studying our planet. It's hard to list the benefits in full, but they include weather monitoring, studies of our climate, including sea level rises, CO2 levels in our atmosphere, tracking aerosol emissions, and seeing the current dimensions of the ice sheets, tracking surface temperatures, crop health, irrigation use, water quality. You can even use precise satellites with cloud penetration to see the hotspots on wildfires, giving firefighters a better chance at tackling blazes. Or we can better understand hurricanes, atmospheric dust clouds, and other disasters. In one incredible application, a NASA satellite intended to study cyclones was used to track locust swarms across eastern Africa, mapping out the most fertile, water-rich areas that locusts like to lay their eggs in or feed in during their juvenile forms. In so doing, they helped reduce swarms in Kenya in 2019, which was incredibly beneficial to farmers and the people whose food they supply. Perhaps the bit that feels uncomfortable is if it seems like the people watching us do not have our immediate benefits at heart. Studying the planet feels like a positive and worthy goal, and accurate data is helpful in that. However, it's also undeniable that businesses across the world would love to keep track of where people are shopping, population trends, and other metrics that allow them to better sell to customers, which is a goal you're less likely to want to sacrifice your own privacy for. Monitoring might help city planners to keep track of the flow of traffic on roads and get a better sense of where to build relief roads or other helpful interventions. Spy and law enforcement agencies also, in fairness, do a lot of good. They stop terrorism and catch criminals. But it's scary to think that once the technology is here, if ever the government in possession of it decides to use it for more invasive goals, there's not much that can be done to stop them. At the end of the day, perhaps this is something inevitable that we will all simply have to get used to. It's difficult to stop the flow of progress. As long as there are advantages to better resolutions on satellites, people will want to pursue developing them. In any case, it's at least good to know just how effective it's all becoming, because then your decisions on the matter can be informed too. You can decide whether this is becoming something that makes you nervous or something you aren't really bothered about, whether this needs tighter regulation through lawgivers or whether it is a necessary cost to be paid for the ease and security of modern life. Wherever you stand on this matter, best put a brave face on. Smile. After all, you never know who is watching. Imagine 100 nuclear bombs going off at the same time. This was the equivalent force of Hunga Tonga Hunga Haipai, which produced the most atmospheric disturbance ever recorded by modern instruments, and the most powerful eruption since the 1883 Krakatoa eruption. The shockwave from it created a pressure wave that travelled around the globe at least 4 times, and although it wasn't audible for all of that time, it was heard as far away as New Zealand, Australia and Alaska. Just one of the aftershocks sounded like this. It caused a tsunami and devastated the volcanic island it was situated on. The ash and dust blanketed Tonga and was carried through the stratosphere across vast distances. Fortunately, eruptions like this are rare, but it just goes to show, nature's fury should not be underestimated. Imagine you're at home or at the office when the walls of the room you're in start shaking violently. Books fall off the shelves, cabinets threaten to topple over. You quickly realize this is an earthquake, and then you look up and it occurs to you that there is another entire story of building above you. As the walls continue to wobble, you know that should they fall, that roof above you is coming down and you stand a good chance of dying. So you look up as the quake goes on and you wonder, will it hold? Will it hold? When you see the footage from the Japan 2024 Noto Peninsula earthquake that struck in the afternoon on New Year's Day, when families were gathered in their homes, it's easy to envision the fear that must have been felt by those who experienced it. This was a deadly tragedy, with 241 people killed and 1,296 injured. In spite of its relatively small size, Japan is the country with the 4th largest number of major earthquakes in the world over the last few decades. Our planet Earth is frequently shaken by earthquakes, but there are things about Noto that make it different from any other earthquake that we've seen before. I'm Alex McColgan and you're watching Astrum, and today we'll be entering a world of earthquake swarms and changes to the Earth's rotation, of earthquake shake tables carrying buildings 10 stories high, and a geological mystery that remains unsolved to this day. It's no wonder that Japan is regularly impacted by earthquakes. Japan sits on the western edge of the Ring of Fire, one of the most tectonically active places on Earth. These vast plates of rock and soil constantly and inexorably shift over the course of millions of years, sometimes pulling apart and sometimes moving together. To further complicate matters, Japan sits along the edge of multiple smaller plates at once. The Pacific Plate pushes west and subducts or slides underneath the Philippine Sea Plate and the Okhotsk Plate. But the Amurian Plate also pushes up against the Okhotsk Plate, while the Philippine Plate subducts underneath the Amurian Plate and the smaller Okinawa Plate at the same time. It's a complex geological wrestling match, one which led to the formation of the islands of Japan in the first place, but one that also causes a lot of friction and tension beneath the surface. What happens when the forces at play become too much for the friction that holds it back and things slip? That's when you get earthquakes. However, in the case of the Japan January 2024 earthquake that struck in the Noto Peninsula, it caught locals by surprise. Why? because Noto is not actually on one of the major fault lines, and scientists are not yet quite sure why earthquakes are even happening there. If you map out the location of earthquakes by depth and location over the last 25 years, you can see that they congregate mostly on the eastern side of Japan, where the Pacific plate subducts under the Okhotsk plate. You can even see how earthquakes that are further west are also triggered deeper beneath the ground, representing the fact that the subducting plate has moved further underground with the additional distance. But rather than striking on the eastern side of the island, the January 2024 earthquake hit Noto to the west. There are other peculiarities. Strange things have been happening beneath Noto over the last 3 years. Since 2020, Noto has been experiencing tens of thousands of small earthquakes in a geological event known as an earthquake swarm. But counterintuitively, this consistent rumbling is normally not something to worry about, as several small shakes are better than one big one, and earthquake swarms generally die out quietly rather than producing large earthquakes. Noto's earthquake swarm bucked the scientific models, lasting too long and producing the exceptionally powerful January 2024 earthquake, and scientists do not really know why. The consequences were serious. The January 2024 earthquake was a magnitude 7.5 and struck at 4 PM Japanese time on New Year's Day, when people were gathered in their homes. It was not just one event, but hit with a number of foreshocks and aftershocks. 1,200 of them that ranged across an area over 150 kilometers across. At least 7 were magnitude 5 or higher. 40,000 homes immediately lost power. Roads cracked. Buildings collapsed. The Japanese government quickly issued a tsunami warning across the west coast of Japan, the first waves of which arrived just 1 minute later in Suzu. A wave as high as 5 meters was expected, although most of the footage captured is a wave of only 1 to 2 meters high. Certainly, the force was enough that buildings along the coast were swept away. All told, there were hundreds of deaths and over 1,000 injuries across 6 prefectures and over $18 billion in property damage. The terrain itself bucked and rose. One strange feature of Noto is that there has been an unexplained upswell that has been taking place there beneath the crust since the earthquake swarm started in 2020. The edge of the peninsula has risen by about 3 centimeters since then, indicating something was gathering down there. Perhaps water? Perhaps magma? Scientists aren't really sure. When the earthquake itself hit, however, that's when the peninsula really started to rise. Some sections of the land rose as much as 4 meters, and you can see the effects in these satellite images. The change in the land's elevation altered where the sea met the shore, pushing the coastline back 250 meters, leaving some ports completely cut off from the water. And when this much land moves, it can influence the rotation of the planet itself. Changing the distribution of mass on the planet's surface changes how quickly it spins. In the same way, a ballerina pulling her arms in will rotate faster. In 2011, the magnitude 9 Tohoku earthquake in Japan shortened Earth's day by 1.8 microseconds, or 1.8 millionths of a second. It's not much, and other effects such as differing sea levels also change the Earth's rotation speed, but it's amazing to see how interconnected the planet is. An earthquake in Japan can affect the entire world. No matter where you are, your life was imperceptibly altered by the Noto earthquake. With all of this, it is no wonder that scientists across the globe are working hard to understand the causes of earthquakes. But for those who live under their constant threat, such as for the people in Japan or other countries like Indonesia, China, or Iran, it's also important to defend against their consequences. So in an effort to improve their architectural design to make them more earthquake resistant, Japan's National Research Institute for Earth Science and Disaster Resilience has taken steps such as developing the world's largest earthquake simulator, eDefense. This 20 to 15 meter shake table supports buildings as tall as 10 stories and can use real-life data to simulate the most devastating earthquakes Japan has ever experienced. By testing different designs in the different types of earthquake scenarios, architects have been able to design braces, beams, and metal joints that reinforce traditional Japanese houses, making them more earthquake resistant. It can be the difference between a building staying upright or collapsing entirely. Interestingly, NASA's space program indirectly helped with creating earthquake-resistant buildings in Japan. Consider the Tokyo Skytree, the world's tallest tower at 634 meters, a place I saw with my own eyes once when I was visiting Japan. Given the risk of earthquakes in Tokyo, it was vital that engineers designed a building that could withstand large shakes. They did so using a central 360-meter tall concrete column that sits on 4 massive rubber bearings, which attaches to the building around it using fluid dampeners developed during the NASA Apollo program. When an earthquake strikes, these fluid dampeners cause the central column to sway at a different rate to the exoskeleton of the building around it. The different rhythms of motion counteract each other, reducing the motion in the building overall. Incredibly, these effects can reduce the force of earthquakes by up to 50%. Earthquakes can carry a terrible cost in lives and destroyed homes and livelihoods. For the Noto Peninsula, the people there have slowly begun the task of rebuilding their lives. Although the broken roads initially made it difficult for emergency services and repair workers to get around, power has been restored to the majority of the 40,000 homes that were affected. Although, as of March 2024, 790 still were without electricity, 18,880 were without water, and 11,400 people were still in evacuation shelters in Ishikawa Prefecture. Earthquakes are overwhelming examples of the natural force that exists beneath us at all times. They can shatter cities, and recovering from them is a slow task. But it speaks to the hardiness and determination of the people who make places like Japan their home. They seek to find solutions to powerful earthquakes to predict them and to mitigate their damage with clever engineering. This can help us all. Through studying the processes that take place beneath our feet, we can better navigate this world that we live on in a way that helps us thrive. The world is dangerous, but also beautiful, and like life, its face is ever-changing. It's up to us to face that change until we can overcome any disaster that befalls us. You may have noticed this video didn't have any sponsors, and that's because it was brought to you by our astronauts on Patreon. Consider joining our Patreon to keep these videos thriving, even when they're sponsor-free. It's the reason we can research deep into the topics we love without cutting corners or chasing clicks. Every new astronaut allows us to explore bigger ideas and make every upload even better than the last. So if you've ever thought about being a bigger part of this channel, join the crew to power Astrum and keep space curiosity alive.